I'll just start off by acknowledging the people that contributed to this work. So the topic of this talk, as you just heard about, is ultra-high resolution fMRI. And this technique is especially exciting because nowadays we can achieve three criteria: not only high resolution, but also high spatial coverage and high signal-to-noise ratio. For example, this is a standard resolution fMRI slice acquired at 3 Tesla, and here's a high resolution slice. So you can see by eye that there's much more fine-scale detail. And not only can we measure this one slice, we can measure many slices using multiband acquisition. Now, from the point of view of a neuroscientist, of which I am one, this is exciting because it suggests we can measure non-invasively activity at the columnar and laminar scale across a large swath of cortex in humans. Now, many studies have already used ultra-high resolution fMRI. What we did was to set out to collect some data of our own with the goal of understanding the nature of the data, and specifically whether ultra-high resolution fMRI can be routinely used for neuroscience studies. Our work involved developing methods and analysis tools and careful evaluation of data quality. Ultimately, our concerns boil down to a simple question: can we accurately measure fine-scale neural activity using this technique? And I should mention that we recently posted a preprint on bioRxiv that covers everything you're going to hear about in this talk. We ran a simple visual experiment. There were 5 stimulus categories presented in 4-second trials. We collected 144 trials, and this took about an hour for each subject. Now, in terms of the data acquisition, we did gradient echo EPI. This was done at 7 Tesla. The resolution, nominal resolution, was 0.8 millimeters isotropic, and the TR was roughly 2 seconds. We used multiband factor 2. This allowed us to cover the entire back of the brain. We also collected field maps. We collected multiple field maps over the course of each scan session in order to correct for EPI distortion. And in addition, we collected standard T1 and T2 weighted anatomical data. Now, in terms of the data analysis, there are many details. I refer you to the preprint to see all the details. I just want to briefly go over the main steps. We use FreeSurfer to generate cortical surface representations. We use these time-varying field map estimates to precisely correct for EPI distortion. And finally, in terms of pre-processing the functional volumes, we do 2 steps. One temporal step to correct for differences in slice acquisition times, and a second step to correct for head motion and distortion, as well as getting the functional data onto these cortical surface representations. This was all done in a single spatial interpolation operation. Okay, so let's turn to the results. The first result is that indeed we can reliably measure fine-scale bold activity patterns. And this, let's see an example of this. Here's a posterior view of the inflated cortical surface for a subject, and different visual areas are depicted by the different colors. Now let's see the exact same thing but on a spherical representation. Now, before we look at functional activity, let's look at some random data. So this is useful because this shows us the theoretical limit to the detail that we could potentially see given our analysis and visualization approach. Notice it's very fine detailed. Now let's turn to some empirical results. This is a map of bold activity. For each surface vertex, I'm showing you percent signal change evoked by the face stimulus category in our experiment. Turns out for this data set and for all of our subjects, we divided it to 6 independent parts, so we in effect have 6 independent measurements. This is actually the first of 6, so I'm going to show you the second, third, fourth, fifth, and sixth, and then the average across the 6 measurements. So let me do that one more time. So here's the theoretical limit, and then here are the actual maps of bold activity patterns: 1, 2, 3, 4, 5, 6, and then the average. As you can see by eye, there is a lot of reproducible fine-scale detail in these images, and that's a good thing. Now, we can compare this to what happens at low resolution. So for this subject, we acquired 2.4 millimeter measurements. This was done at 3 Tesla, and the exact same experiment, exact same analysis and pre-processing and visualization, and this is how that looks. We can flip between the two. This is the 0.8 millimeter acquisition. Here's the 2.4. So you can appreciate by eye that there appears to be a lot more detail in the high resolution measurements, and this is a good thing. Okay, so we can make reliable fine-scale measurements of bold activity patterns. Our second result is something completely different, but also important. and it's a complicated spatial effect that stems from the convoluted structure of cortex. We refer to this as curvature causing distortion. So let's try to unpack what this means. So here is a flat patch, or a flattened section of cortex in ventral temporal cortex, and we're looking at sulci and gyri. And in this analysis, we want to understand the physical units of our measurement process. And to do that, we devised a technique which we call surface voxels. Basically, we take a volume with known spatial dimensions, and we sample that volume onto our surfaces using nearest neighbor interpolation. So let's see an example. Here are 2 millimeter voxels being sampled onto the white matter surface. Each little color patch represents, in effect, the cross-section of an individual voxel. And if you look at this, the color patches are relatively homogeneous in size and shape. So everything is making sense. But something strange starts to happen if we look at other cortical depths. So we do the exact same technique, but sample onto the peel surface. As you can see, there are regions undergoing substantial compression and expansion. So let's zoom in a little bit to see how this works. This effect is tied to curvature, so I summarize this as follows. In the middle here, you see a gyrus, and this will undergo apparent compression, whereas the sulci in either the left and right will undergo apparent expansion. So again, sampling onto the white matter surface, and as we progress up through the cortical thickness, we see apparent compression and expansion. So why does this effect occur? Well, let's look at cortical surfaces. So in this representation, I draw your attention to the gyrus, for example, on the right. On the gyrus, let's consider what happens when we move from the inner to outer depths. So the blue, for example, up through orange. As we progress from inner to outer on a gyrus, the cortical surface area is necessarily increasing. And what this means is for a nominal voxel position in an outer depth, this voxel will have to undergo some shrinkage to match what we observe at inner depths. Now the reverse happens for a sulcus. So in the middle of this visualization, you see a sulcus. Again, as we progress from inner to outer depths, that's blue up through orange, you see the cortical surface area is dramatically decreasing. And what this means is a nominal voxel position in the outer depths is necessarily have to expand to match what we observe at inner depths. So this is a little peculiar, and it'll take a little while to wrap your head around it, but the point is that local cortical curvature is going to introduce inevitably weird effects. Specifically, you're going to have a change or a variation in effective spatial resolution, and you also will have weird artifacts or distortions in visualizations when we stare at these very high resolution maps of activity. Okay, so let's turn to the last result, and that has to do with the impact of veins. Veins have long been recognized as degrading the specificity of fMRI. And with our data set, we have the unique opportunity to assess these effects across a large sections of cortex measured at a very fine scale. We find that veins cause extensive effects in our data set. Let's see an example. Here's a posterior view of a spherical surface. And this is simply a map of EPI intensity. This is just the raw signal intensity. And this is actually a movie because I'm going to show you this as a function of cortical depth. So in this movie, we're sampling deep up through the superficial depth levels. Let me play that again. And you can just see from this visualization that not only is a lot of cortex darkened in this visualization, but these effects increase dramatically when we sample near the superficial depths. This is not surprising if for those who understand what's happening. And the reason is that veins are causing these effects, and they tend to be placed on the surface of the brain. Let's see that in a little more detail. Here's a volumetric visualization, T1 and T2, and the EPI volume. This is just the raw EPI volume averaged across the experiment. And you can see, if you look closely, dark spots, and it's known that these dark spots reflect susceptibility effects due to veins. And we can confirm with our surface-based processing, and we do some thresholding, that we can confirm that these effects, are in, these effects are in anatomically appropriate locations in gray matter and not an artifact of misregistration or things of that nature. Not only are veins causing extensive effects in our data set, there's also systematic bias in where they're located. Here we're showing percentage of vertices, surface vertices, that are deemed to be dark as a function of cortical depth, and we plot this separately for sulci and gyri. As you can see, there's a strong bias for these dark vertices to be located in superficial depths, not surprisingly, but there's also some bias for them to be located in gyri, and this effect replicates across all subjects. Now, we can also look at venous effects across the cortical surface. Here's a visualization of the FS average space, and I'm showing you first what happens for cortical curvature. So these are independent subjects aligned through FS average, and then the last frame will be the average across subjects. So not surprisingly, because of the nature of FS average, that these effects do align to some degree across subjects. Now we can repeat this analysis for our maps of venous effects, and here's the result using a slightly different color map. You can appreciate by eye that there is a substantial degree of consistency in where these effects occur. And in fact, the level of consistency approaches that we observe for cortical curvature. I should mention in the paper we are quantitative about these things, but I want to just show you pretty pictures here because they're pretty. Okay, so venous effects are extensive. They tend to occur in systematic locations, therefore they don't quote unquote average out if you average across subjects. And most critically, they exert substantial influence on the fMRI responses that we're interested in as neuroscientists. Let's see an example. Here's a zoomed in view of some cortex. Notice the scale bar. And here's a map of EPI intensity that we've already looked at. This is the intricate pattern of vasculature that we can see in this subject. And now let's look at bold responses evoked by our experiment. This is simply percent signal change averaged across stimuli. And if you stare at this, you see that regions exhibiting large percent signal change, specifically the yellow regions, bear a very strong relationship to the pattern of vasculature. Thus, the structure of the vasculature appears to control how bold activity patterns are being manifested in our data. To drive this correspondence home, let's look at a volumetric visualization. Here is a minimum intensity projection. So we basically define a small slab, 1 centimeter thick, and we compute the minimum intensity observed in our fMRI data. So you can see in this visualization the snake-like structure of the vasculature, so we can just see it by eye. And now let's compare this to bold responses. This is a maximum intensity projection. Basically, for each pixel, compute the maximum percent signal change across our 1 centimeter slab. And if I flip between these two, the EPI intensity and the bold responses, you see a very striking correspondence indicating again, the influence of the vasculature. So, to conclude, we believe that in our hands, given our acquisition and our analysis methods, that we are making accurate and reliable measurements of fine-scale bold activity. However, given the systemic influence of veins, it is not clear whether this is providing accurate reflections of local neural activity. In the course of the study, we've demonstrated some practical strategies for understanding these effects, including the surface voxels technique, which allows us to understand these peculiar distortion effects, as well as the use of EPI intensity as a very simple metric to at least track where the locations of these effects are. Now, there are ideas in the literature for how we deal with this problem of veins. We do discuss this in the preprint. I don't have time to talk about that right now. I'm not sure any of them are fully satisfactory. However, we are working on a new technique, and that's in progress, and you'll have to wait till next year to hear about it. Thank you for your attention.